if you look at the system, you have an input, it's a sinusoidal. It will never actually be zero at the steady state. It's going to always oscillate in the input. It's a first order system. The output eventually is also going to be a sinusoidal with the same frequency omega as the input. The magnitude and phase will be different. Typically, whenever you apply a signal into a system, let's say even a step signal, you would imagine some transient response. You would imagine the system, even if it's a step, simple step, the system wouldn't be able to catch up with you at the beginning. Instead, it might do something like this. So there is this transient period. And in the case of sinusoidal signal, there will also be a transient. The output is not really a pure sinusoidal. Now the problem says, if you look at the system, and then there are some very special initial conditions. There is this very special initial condition that will make your output completely sinusoidal. There will be no transient at all. Your output will immediately start to behave as a sinusoidal, which is amazing, which is in many applications very much desired. You have an input, the output just tracks the input shape. To actually understand the problem, I would like to dig a little bit deeper into the state space equation solution. We have a typical continuous time state equation, x dot equals ax plus bu. We have discussed that the solution in the time domain is xt contains the free response e to the power of at times the initial condition plus the forced response, which is dependent upon the input u, and it's an integral containing exponential functions as well, and B matrix and A matrix. The solution can also be discussed from the Laplace domain. Looking at this equation, we can apply Laplace transform and obtain S capital X of S minus X0 equals A capital XS plus B U capital US. And from there, you can derive in the Laplace domain, capital X of S is Si minus A inverse X0. This is the free response in the Laplace domain, and then a forced response, Si minus A inverse B US. Now, pay attention. Although this is the term that contains the initial condition X0 here, this is not the transient response. This integral over here, it will also create some transient. Even for the sinusoidal signal term, it will also be some transient. Let's say something like this. Initially, it might go down like this, and then gradually it becomes sinusoidal. This transient response, the main observation is that it depends on the input as well as the initial condition. Let me show you how it actually looks like. I have actually coded the problem in here in MATLAB. We have a first order system. A is -1, B is 1, as the same numbers in your homework. So you can see transfer function we can easily obtain is 1 over S plus 1. In the state space, I use the command TF to SS, which takes the numerator and denominator of the transfer function and then spits out ABCD matrices. And then I define G as the state space, continuous time state space model. All right, so let me run the first few blocks. So if I run, now this command is showing me, I assign the initial condition, I just pick one, some random numbers. Let's say the initial condition X0 is 1, and then I simulate the system LSIM with the input U and simulation time interval T sim, and then initial condition x0. So these are defined actually here. I calculated T sim from 0 to the time constant, 30 times the time constant of the system. And then I set omega to be 5. U input is a sinusoidal with omega as the frequency. So you can plot, and this is the response, right? So it's a sinusoidal, pure sinusoidal signal. Magnitude is 1. And then simulation time is 30 seconds. The output with initial condition 1, this is a live output. You can see it actually contains some transient response. It starts at initial condition is indeed at 1 in the red line over here, red dashed line over here. Let's verify. Actually, we'll show that later. If the initial condition changes to, let's say, larger value, then you can see the response will be more aggressive at the beginning. It starts from far away, from 10 all the way to finally becoming a sinusoidal. So the transfer function, the system is indeed pretty powerful. It can drag the system from an initial condition that's very far away from 0 to become a sinusoidal. Now, I can change the initial condition. Let me change it. I can do many numbers, and you can see initial value -5, initial value 4, right? I can even say initial value 0 here. This is the initial value -1, 1, 0. So even if I set the initial condition to be 0, you can see the output actually, there's still some transient, right? Even if it starts at 0, it's not a sinusoidal, pure sinusoidal at the beginning. It has this transient response. So that verifies that even if you have 0 initial condition, you can have a transient response. Now the problem actually guides you to a very special initial condition that I calculated over here. Okay, so this is a little bit easier to view. The output is purely sinusoidal. So that is this problem over here, a very simple problem, but it actually implies a class of control design algorithm. There is this class of algorithm that will focus on assigning these very special initial conditions so that the output will have as minimum transient as possible. Let's look a little bit into the problem itself. In order to find this very special initial condition x0, let us do some analysis. There are different ways to do this. What I will show today is the Laplace domain solution. We can see that in the Laplace domain, we have this easy Laplace transform of capital X of S. It can be written this way. It's 1, if you solve this equation, you will see it's 1 over S minus A x0 plus 1 over S minus A B U of S. Over here, when input U is a sinusoidal, US becomes what? Omega over S squared plus omega squared. So therefore, this term, it equals BS minus A omega S squared plus omega squared. And after applying partial fraction expansion, we can separate this into 2 terms. One is a first order term, another is a second order term. So second order term, let's say the numerator is K1S plus K2. This is the most general form of the numerator. And then let's say the first order term has a numerator K3. At this point, if I think about the problem is asking me, under what kind of initial condition will I be able to have x that is purely sinusoidal, right? So looking at this, I can see that this will give me purely sinusoidal, right? Only the first two terms are not sinusoidal. So if I just want to know what kind of initial condition will give me a pure sinusoidal output, actually, I only need to care about case 3. I don't have to know K1, K2 in order to know the initial condition. That analysis saves some computations. Case 3 from partial fraction expansion is the limit of S approaching A, and then this term multiplying S minus A. So partial fraction expansion gives us this term is B omega A squared plus omega squared. Comparing this term and this term, we can see that for this transient to completely disappear, x0 must be equal to negative of case 3. So x0 must be negative b omega a square plus omega square. So that's the special initial condition that I showed in MATLAB. It depends on the input, omega frequency, and depends on the coefficients of the system, A square, A and B.